Fortunately, they were in the printer right next door. So basically, we were talking about strings and light cone coordinates and so forth. I'm going to try a new kind of chalk. The student erased the last lecture, and that's why there isn't a lecture 14, so this is lecture 15. Let me just remind you what light cone coordinates are. It's one of the inventions of, one of the many inventions of Paul Dirac. So you pick one space dimension, and associated with time, you call that x plus. The other one is x minus. Similar equation for p. Okay, then there's a class of gauges. Well, let me just say this: that in theories, in simple theories like ordinary quantum mechanics, ordinary, and I emphasize ordinary quantum mechanics. First semester quantum mechanics. There's no extra symmetry that confuses things, and instead one just has x and p, and one has a commutation relation for x and p. As soon as you introduce the electromagnetic field, though, you introduce an extra symmetry, which we call gauge symmetry, and there one has to choose a gauge in which to quantize. And the simplest gauge is the Coulomb gauge, but of course there are other gauges. With strings, you have reparametrization invariance, which means that you can change what you mean by sigma and tau at will, and the equations have to remain the same apart from primes everywhere. And so what one does is one imposes a class of gauges. This is in, so let me just say this is more general than light cone quantization. The conditions are x is the, are all the coordinates of the string. And we set that equal to beta, something called the string tension, n dot p. N is a vector, and I should have said whether it's space like or time like. I think it's space like, but let me go on. N dot p is 2 pi over beta n dot, and this is that momentum vector p tau. Remember that was, in the case of an M-Gato string, it's so very complicated. Let's see. One of the choices is when n gives you x plus, and so there is the vector n would be 1, 1, and then all zeros. So that's a like vector, isn't it? Yeah. Okay, so n may be a like vector. Okay. It certainly is for the light cone gauge. Okay, so there's a whole class of gauges. Beta, you might, what is alpha? Alpha is the string tension. And beta is 1 or 2, and it's a 1 for closed strings, and it's 2 for open strings. Do you think I should use the bigger chalk? Would that be better, or is this okay?
I think that's okay.
All right. Okay, now it turns out that these conditions imply certain constraints. X dot plus or minus x prime squared is equal to 0. And this simplifies the momentum densities. P sigma mu is then minus 1 over 2 pi alpha prime x mu prime. Prime here means, I don't know why, I mean, give me a break. Why did they introduce an alpha and then throw it out and just use alpha prime? I don't know. It doesn't mean derivative with respect to sigma. Over here, the prime does mean derivative with respect to sigma. So the string theorists really need to clean up their act on notation. P of tau and mu is then 1 over 2 pi alpha prime, and now we have x dot mu, so that's the time derivative. Now the remarkable thing is that in these gauges, the coordinates, instead of obeying the very complicated nonlinear equations that we saw when we had the Navigato string, we actually have something very simple. A wave equation, x double dot mu minus x double prime mu equals 0. So these coordinates of the string obey the wave equation. So this makes things a great deal simpler. I said the tension of T was alpha prime. Instead, the tension actually is T0 is 1 over 2 pi alpha prime. There. Open strings then have a certain parametrization, and this is a long equation, so I'm going to go over to this board and write it down. It's x mu of tau and sigma is equal to x0 mu. So that's basically where that tells you where the string is on average, say. Or at least, actually, that's a fixed time, and so, I mean, there's no sigma tau, so this is where this is sort of the center of mass of the string, but at tau equals 0. And then we have the square root of 2 alpha prime. Alpha 0 mu times tau. And so this is how the center of mass is moving with time. And then we have an I, the square root of 2 alpha prime, and then a sum. For n not equal to 0, and it's e to the minus in tau over n, alpha mu n cosine n tau. And I should say this is for open strings. So let me just remind you that an open string looks like that. For closed strings, they look like that. And so there's when sigma is 2 pi, I forgot to mention that we're now considering sigma to be 0 to pi, so I shouldn't have said 2 pi. And sigma and tau are both dimensionless now after we've imposed these gauge conditions and so forth. Okay, so that's open strings. The closed strings are kind of similar. They're pretty similar, but there's an essential difference. The 2 is just because we're going from cosine to something else. Okay, so in closed strings, there's a distinction between left moving and right moving. And here's an extra.
I could have done something.
that I didn't realize was there. So this is for closed strings, and you have left movers and right movers, and you have to distinguish between the two. And I guess you can. The notion of the distinction is that one kind moves, as you increase sigma, the wave moves that way. And the other one goes in the direction of decreasing sigma, negative sigma. With an open string, you can just turn the thing around, and so you can't distinguish between left movers and right movers. So that's how that basically comes about. Now, so far we're just in this class of gauges, sort of a generalized light cone gauge. If we impose the light cone gauge, then what we have is x plus, which of course is x0 plus x1 over square root of 2, is now equal to this thing. Beta alpha prime p plus, where p plus is p0 plus p1 over root 2. And in fact, there's a formula for p plus. The p plus is equal to 2 pi over beta, this complicated p tau plus, the one that we saw in the one that was derived canonically as partial Lagrangian with respect to x dot, in this case plus, I guess, or maybe minus. With light cone gauge, sometimes switch from plus to minus when you change from vector to a derivative. Anyway, there are then some relations, namely that x plus prime is equal to 0. So x plus doesn't change with sigma, and x dot plus turns out to be beta alpha prime p plus. So these are relations that come about in the light cone gauge for this come about in general for the light cone gauge. Now, if we go back to these open strings, so for the open case, and I'm only going to discuss open strings briefly. The closed string case is analogous apart from certain differences, and I don't think, since we're just trying to cover all the string theory in a couple of lectures, I don't think we need to go into that detail. But for open strings at least, this x plus 0 and alpha plus n is 0, here for n not equal to 0. And moreover, square root of 2 alpha prime alpha minus n is 1 over 2 p plus, and then a sum on all p, p's are integers here, alpha j n minus p alpha j p. So over all integers, j labels the transverse coordinates now. So we have x0, x1, and then the others. The other 24. And this thing is defined to be 1 over 2 p plus L perp n. And this thing is called a Virasoro mode. And classically, you can say that the mass squared of this string is 1 over alpha prime, sum on n from 1 to infinity, alpha n L squared. Okay, so that's the classical situation. If we now go to quantize the string, in light cone gauge, what one does is impose these commutation relations. Xi These are equal time commutation relations. Remember, in quantum mechanics, you don't need to say equal time, but in quantum field theory, you always impose equal time commutation relations. And the idea is that at the same time, fields at different points in space are independent, and consequently, at each point, you have a quantum system, phi and pi, and at the same time, they have the XP commutation relations, apart from a delta function. And so this is P tau j of tau and sigma prime, so a different point on the string at the same time. And this is I eta ij delta of sigma minus sigma prime. Now these are, again, equal time or equal tau commutation relations. And they vanish unless the point on the string, the 2 points are equal. In a sense, they're equal sigma commutation relations because otherwise it's 0. But never mind. I shouldn't try to make jokes. I'm dealing with something that's complicated. This commutation relation for open strings, you can achieve it by requiring the alphas to obey certain rules. And these things are effectively Fourier coefficients. So you have alpha m I, alpha j n is m. Now that's quite a surprise, the m. The m there is probably because of this 1 over n. Eta ij, and then times delta sub m plus n, comma, 0. So if m is minus n, then you have something non-zero. These are for the transverse modes. And eta is minus 1, 1, 1, 1, and so forth. So there are 25 ones and 1 minus 1. Of course, at this stage of string theory, one doesn't know how many dimensions there are. One is just quantizing in an arbitrary number. I'm skipping, of course, an enormous amount of detail. Now, in this case, one is able to write down a Hamiltonian, and the Hamiltonian is the quantum version of the Virasoro operator, the 0 quant, minus 1. And so this is a pretty remarkable relation. So you might say, where does it come from? Well, it comes from, first of all, the standard manipulations where you say, well, we have the conjugate momenta, so the Hamiltonian is P Q dot minus L, and you do the analog here is P X dot minus the L of the action, and then you impose Lorentz invariance, and that's a long story that I'm skipping how you impose it. But by imposing Lorentz invariance, one finds 2 things. One finds that this is the Hamiltonian, and in particular that D is equal to 26. And also, before imposing Lorentz invariance, this thing looked like that minus A. One didn't know what A is. Now A is minus 1. Okay. All right, so this theory, though, does have certain problems. Problem 1, the main problem is that it has a tachyon. That is to say, particles that move faster than light. So this is bad. The second thing is that, what is this theory? Well, this theory is essentially a 2-dimensional quantum field theory, X of tau and sigma. And it's quantized, I mean, apart from all the stringiness, it's effectively a two-dimensional quantum field theory, and consequently it has divergences like any simple quantum field theory. And now a standard quantum field theory in 4 dimensions of space-time has an energy divergence that goes as the 4th power of infinity. In other words, it diverges as, if you write down the energy, you get something that is infinity to the 4th power, or your cutoff, your ultraviolet cutoff to the 4th power. If you're in 3 space-time dimensions, it's infinity cubed. Here we have 2 space-time dimensions, space-time in the sense of sigma tau. The dimensions of the space-time in which the coordinates, in which the string moves, that's 26. But the dimensions of the space-time of the quantum field theory is 2, sigma and tau, sigma being space, tau being time. And so what you have is a quadratically divergent theory. And so string theorists, we normalize this by saying the sum n equals 1 to infinity is equal to minus 1 over 12. So, but this is, so I mean, there's a good side and a bad side to this. The good side is that, well, in all of these quantum field theories, that at least all of the simple quantum field theories are analogous infinities, and as I said, they vary with the space-time dimension. You can take 2 attitudes toward them. One is that we don't have the right theory, and the other is, well, we surely don't have the right theory. There's no doubt about that. The question is, do we have any hope of finding a theory that makes these things finite? We don't know. David and I are working on that, but good luck. All right. Anyway, the other issue is that we can say, well, all right, at this stage of human evolution, we don't know what the true finite theory is, so we'll say there is some theory, and we don't understand it, and it does whatever it does, and our quantum field theory gets us from some high energy down to some lower energy, and or from some ordinary momentum up to some other momentum, and in this way, and so that the way we implement that mathematically is called renormalization. You basically cancel all the bad infinities in an organized way with respect to the symmetries of the theory. Okay. Okay. So what is the next thing that one does? Well, the next thing is to add supersymmetry to the theory. If you write the ordinary action S, and you can write it as an integral d tau, integral d sigma, and you can write this as, I'm going to write them as J because this capital I is a pretty weird notation. Well, I don't know why it's just in square though, so it's just stupid. But anyway. Okay, so this is the action in the light cone gauge, and one adds to it a fermionic action. And one way of doing that is to write, well, let's see, I don't need to write another integral. Well, I do have this alpha prime, so I better write it as alpha prime or 2 alpha primes times, and then it's psi J1 toward derivative plus sigma derivative. So this is a light cone structure here. Psi 1 J plus psi 2J toward derivative minus sigma derivative psi 2J. Okay, so what's happened here is that one has added 2 fermionic degrees of freedom in the sense of these two for every transverse coordinate in a way such that this and that kind of look the same, and in fact the action can be said to be supersymmetric in the sense that under supersymmetry transformation, the thing inside the square brackets changes by at most a total derivative, and so it's at most a boundary term. So if you do this, if you make the theory supersymmetric, then this goes down to 10 dimensions, and the tachyon goes away. So that's why people think that that string theory is, why people do supersymmetric string theory. Okay. Let's see, what's the next topic? I guess well, let me say a little bit about there's something called Kovarian string quantization. So far we've been doing things in the light cone gauge, and the advantage of the light cone gauge is that you don't have any, I should get rid of this thing, you don't have any spooky constraints. So in other words, all the operators basically are what they seem to be, and there are some constraints, but that's basically it. On the other hand, if we go to, maybe I should go down to this board here. If we go down to Kovarian, let me see what the time's, I think we have time. If we now do Kovarian quantization, what we do is we write, and now let's go back to ordinary strings rather than so what we have is, well, 1 over 4 pi alpha prime. And now we have the Tor derivative of x upper mu, the Tor derivative of x lower mu, minus the sigma derivative of x mu, the sigma derivative, well, you can, sigma is just, well, we've already, here. That's fine, don't like that. And so this is obviously a much simpler action, and for this action, the P tau mu is just partial of L partial x dot mu, and this is 1 over 2 pi alpha prime x dot mu. So everything looks a lot simpler, and you can wonder why did one ever do the light cone gauge? Well, the commutation relations turn out to be this. These are equal times. Okay, so these look very nice also, but the problem is that whereas in light cone gauge, I and J just went over the transverse space modes, the spatial modes. So eta ij was +1. Here, we're going over mu and nu, all of the directions, including the time direction. So in the time, you get a minus sign here. And that means there are various conceptual problems that introduces. And so it's so what we have then are constraints. So in the old way of doing quantum electrodynamics, before people started to use the Coulomb gauge and started to use path integrals, they had a formalism which I think was called the Gupta-Bloiler formalism. And it had a commutation relation which would have been A mu, the A mu E nu was an I eta mu nu delta, and it had that same problem of a minus sign. And so then there was a constraint that was introduced, and it's a very confusing business. So I think I'll just let that go there. What is simple here is that it's very easy to add in the supersymmetry. In fact, it's probably even easier than here, because here we were restricted to transverse degrees. Also, this J means we're talking about the transverse part of the fermion. So this is a spinner in 26 dimensions, but living on a space-time of 2 dimensions. Anyway, let me now go to what is quite a nice right, okay, here we go. What is, you might say it's sort of this is called the Polyakov action. And what basically one does is one writes this action here in a more suggestive form. One writes S as minus 1 over 4 pi alpha prime integral d tau d sigma, and now eta alpha beta d alpha x mu d beta x nu eta mu nu. So this eta is the flat metric in, say, 26 dimensions, or 10 if you add fermions. And this alpha beta is the metric on this space-time. So eta alpha beta is just equal to minus 1, 1, 0, 0. And okay, so now the trick here is to say, well, we're going to rewrite this. We're going to start from a different place. So let me give you a different place. We're going to say S is instead minus 1 over 4 pi alpha prime integral d4 d sigma. And now we're going to say square root minus h alpha beta d alpha x mu d beta x nu eta mu nu. We're going to allow h to be dynamical. So now this looks like a theory of gravity, but in 2 dimensions. In other words, in the case of gravity, you have ordinary gravity of d4x square root of minus g, where g is the determinant of the space-time metric with lower indices, and then one would have g upper mu nu, but here it's just 2 dimensions. Okay. So that's basically this then is what's called the Polyakov action after a Russian physicist. I don't know where he is now. He probably might get used to advanced study. I don't know. He came over to the States. Plasmos. So one uses various tricks. I'm not going to go through all of the steps, but actually one can go through one of them, though. The variation of the action is essentially minus 1 over 2 pi alpha prime integral d sigma d tau, and square root minus h alpha beta, and then it's d alpha of the change in x mu d beta x mu eta mu nu. So the reason why 4 went to 2 is that you could vary one or the other, and it's symmetric. Are there any questions you guys want? I mean, I'm going over a book this thick in just a couple of lectures. All right. Anyway, you then integrate by parts, and you get a derivative there. And so one of the field equations right away is the alpha derivative, and so the alpha derivative being d by d sigma or d by d tau. The alpha derivative of the square root minus h alpha beta d beta x mu is 0. Okay. Now, in order to vary the metric, one uses this trick, and I'm going to mention what this trick is because it's a famous trick that we all ought to know about. It's in the I remember I was a first-year graduate student when Schwinger mentioned this, and he just mentioned it parenthetically and using it while using it in a derivation. And he just said, variation of the determinant of x is the trace of x inverse. Oh, no, he said the variation of the logarithm of the determinant of x is the trace of x inverse. Variation of x is because it's a logarithm. It kicks out a 1 over determinant. And I just sat there and said, where in God's name did that come from? But since Schwinger said it, we were sure it was right. Okay, well, let me just say that the equation of motion that comes out of varying h is partial alpha of x dotted into partial beta of x minus a half h alpha beta h gamma delta d gamma x dot d beta d delta x equals 0. So that looks sort of complicated, but on the other hand, we can call gamma alpha beta, if we define gamma alpha beta as d alpha x dot d beta x. And this is the thing that occurs is one of the things that occurs in the Namugato action. Then what this equation is really saying and I'm again skipping a lot of steps here, is that H alpha beta is some constant, a positive constant of it's actually 2 sigma for some reason, gamma alpha beta. And what this tells us then is that the original action, and you see there is a, well, yeah, this thing is gamma alpha beta. And so what one finds is that this action actually is minus 1 over 2 pi alpha prime and integral d tau d sigma square root of minus gamma. And this square root of minus gamma, with gamma written this way, is one of the forms of the this is actually the Navigato action. Okay, I think that's enough for that for the moment. This has been a starting point for much of the work on strings. So in other words, one has this sort of nice general relativistic flavor. What one would do then to make it a superstring would be to add to this Fermi things and something like this. Of course, I'm not writing it down correctly, I'm just sort of suggesting what it would be. So you put in fermions to make this action supersymmetric, and then one has a theory without a tachyon, consistent in 10 dimensions, which is what we had back there. Now, what do string theorists actually do with this? The press from Brian Greene and others is that it's a theory free of infinities. Well, it really isn't a theory free of infinities. You still have the infinities of two-dimensional quantum field theory, which you just renormalized. Moreover, it's what the people do in practice is they say, well, we're not going to try to do a quantum field theory because they don't actually have a quantum field theory of strings. Instead, the string itself is a quantum field theory. So a quantum field theory of strings would be a quantum field theory of quantum field theories. And they haven't gotten there yet. And in fact, they've been trying for decades. What they've decided then is, okay, we're not going to try to do a quantum field theory of quantum field theories. We're going to try to do a string theory of the S matrix. And so these diagrams that you see that look like this, if time is going this way, this is one string, one open string with another open string collide and then go out. This gives you an S matrix amplitude. And the S matrix amplitudes that you get are finite. And of course you can also have, you can imagine that this thing is a closed string. And so it goes out like that. So you can do that. And then you can have the thing be more complicated. This is two to two scattering. You can do end to end. And the procedures that are used are basically, as far as I understand it, it's a Polyakov action, supersymmetric, and what turns out to be true is that, well, you might say, well, what would this be? This would be some sort of a path integral. So you'd be doing some sort of an integral over all kinds of surfaces like this. Okay. In other words, the classical action of this thing is basically the area of this thing. Well, because of the reparametrization invariance, you can express all of those actions. They're all effective, not all of them the same, but a whole class of them that you normally integrate over are the same. And so what you have is simply an integral instead of over, I mean, you might think that you have to path integrate over this point, the string coordinates at this point, at that point, and the other point, at all points in the two-dimensional quantum field theory. So in other words, you might think that you have to do a product of d mu product over sigma tau of dx mu of sigma tau. That's what you think. But instead, e to the minus s if we're in Euclidean space. But because of all the symmetry, this thing turns into just an integral from sigma 0 to pi. And in other words, they turn out to be an integral over a finite number of variables. And so that means that you can actually do them, and moreover that you verify that the amplitude is finite. So that's the situation. The impression I get from talking with people is that a lot of the enthusiasm has gone out of the field of string theory. And in fact, it's also true that what's happened here is that theoretical physics has gone into a kind of loop. And back in the 60s, Mandelstam and Chu and Frautschi and Redjay and so forth were using, and Henry Stapp at LBL were using analyticity and unitarity to say things about scattering amplitudes. This then gave rise to string theory in the 60s, and then it sort of went to sleep, and then it resurrected or reawakened in the mid-'80s as a theory of gravity or a theory of everything. And now it's come around, and over here it was just an S-matrix theory. They gave up quantum field theory. They were just using analyticity, unitarity, Lorentz invariance, and trying to calculate the S-matrix just from these almost philosophical and very mathematical propositions. Well, we come all the way around, and the string theorists say, well, we're just computing the S-matrix. And the problem they have is that, I guess, it's that there just isn't enough variety. In other words, the theories of these supersymmetric, these string theories are so constrained that you just have a couple of them, well, maybe 5 of them, and and even though there are just a few of them, yeah, what I haven't said is, okay, this is the S-matrix theory. What happens to all those extra dimensions? And I've been thinking lately that in as much as in quantum field theory, in gravity, it's natural to embed the space-time manifold of 4 dimensions in a higher dimensional infinite space-time of however many dimensions you need. So I'm not bothered by extra infinite dimensions, but almost everybody else is, and they then ask, well, how can we compactify these extra dimensions? It turns out there are almost infinitely many ways. I think it's 10 to the 500 or something, as is an estimate. And so as a result, the predictive power is essentially 0. And I think the predictive power is 0 because the theories are so constrained. Whereas in quantum field theory, in fact, if you go to the standard model, we have quantum field theory in which we have, I don't know, maybe 30 arbitrary parameters that we put in to get connection with the experiment. Most of those are masses of the fermions. And And the theory, the quantum field theory, is sufficiently flexible that you can just stick in all those 30 parameters. In the case of string theory, there are hardly any parameters, and there's hardly any variety, and so you don't have anything to pick out the one cosmology out of 10 to the 500 cosmologies. Now, some people have thought of this as a virtue, and one of the first to do that might have been Steven Weinberg. His view was, well, we have this cosmological constant problem, which is that the energy of the vacuum is a small value, not zero, and consistent with universes that live either infinitely long or at least very long. And whereas if the energy of the vacuum were much higher, and positive, it would have, the universe would have been, the expansion of the universe would have accelerated from day one, and we couldn't even, I mean, things would be just so spread out that gas never would have collapsed to form stars. You just have an incredibly dilute space-time of, we're lucky to have hydrogen atoms. It might have helium atoms, but that's about it. And so the idea is that the puzzle then is, why is the cosmological constant so small? And the anthropic answer is, well, there are actually 10 to the 500 possible universes. Intelligent life only grows up in the ones where the cosmological constant is appropriately small, and that's why it's small, because we're here. You may or may not like that, and I'm not sure how I feel. I don't think I like it very much. Anyway, the term that most people use is the multiverse, but Leonard Susskind uses a much better term. He calls it the megaverse. Mega, first of all, is a million, multi is just 1,000, and if it's 10 to the 500, you should certainly opt for mega. Also, megaverse sounds much nicer than multiverse. Multiverse is kind of a mouthful, it's a stupid term. I think that's about it. But if you guys have questions, this must have been just too much too fast.
Your reference was, is it Zweibach or is it?
Zwieback. Well, that's the German pronunciation.
Yeah.
Zwieback. It's a Cambridge book, S-W-I-E. I think it's B-A-C-H.
Okay.
And there's a second edition. You can also download it for free from ebooks. No, it's bookzz.org.
Okay.
But then, you just have an electronic copy. You don't need the actual physical book. Cambridge did a nice job printing the thing. Yeah, so I think I'm going to call it quits here for strings. How many more lectures do we have? This is formally the last lecture, but I could give another lecture during exam week if you want. But so why don't you vote on it? Maybe I should turn around and tell me what.
I'm exam free, so it doesn't matter to me.
I have one on Tuesday, but it's not like super stressful. So yeah, I'd be okay with that.
So it's okay to talk Wednesday?
Yeah.
All right. So I give a last lecture. But what do you want it on?
The renormalization group chapter is kind of short. Is that something?
All right.
I mean, page-wise, it's short. 10, 12 pages.
Okay, let's do the renormalization group thing, because there's actually something there that I've been thinking of publishing for about 4 years.
Okay. Is that okay?
Yeah.
All right, so why don't you turn it on?